Right, so I'm the last talk, and yes, I am representing a team here, this SPEC HPG team, who has been working very hard over the last year and a half or 2 years on coming up with our first official OpenMP 4.5 benchmark. And for that, we have an effort within the ACCEL effort in SPEC HPG that we just are very happy to announce that we just released this benchmark. And the goal of this benchmark is to make sure that compilers can optimize OpenMP the best way possible while targeting a programming model that is performance portable. The outline of my talk is going to pretty much be an overview of the effort that we have at SPEC HPG, the benchmark philosophy. I want to talk a little briefly about the SPEC ACCEL 1.2 benchmark, which is the one that contains OpenMP 4.5 offload support. We're going to have some, I'm going to talk a little bit more about the experience that we have in producing this benchmark, and this is, and we're going to provide some our experience and feedback that we would like to tell to the community, so that when they have like similar codes, they know what to do based on our experience. And then some feedback that we would like to give to the OpenMP organization as a team to make things better. So SPEC HPG is part of SPEC, which is a non-profit organization that was established to standardize benchmarks, and it's composed by many groups, and one of the groups is the high performance group, which Oak Ridge is part of. And we participate with many vendors and universities and national labs in this effort. The ones that we're, the people who develop these benchmarks are the ones here with their logos. And I just want to mention that this is a very important venue that I find it like very, very interesting, because from the perspective of having my OpenMP hat, I can see that we have a lot of collaborations like this in terms of OpenMP ARB, but also having a collaboration like this to interpret and use the specification is very important. So it's also a good idea for people to also get involved in this sort of effort, because we can learn from this process, as well as help to co-design ideas with OpenMP ARB, as well as develop benchmarks that are going to be used by the vendors to optimize on their platforms. So there is always when we develop these benchmarks, we develop a score, and this score is kind of like has a relation, or is a ratio with a reference machine. And for example, the SPEC ACCEL 1.2 benchmark, or the OpenMP benchmark, is based on the reference machine, which is an SGI machine, and all the measurements that we present here is based on that. So the benchmarks are kind of like full applications, and we try to bring a lot of the overhead from, including all the overhead from real applications. So it's kind of like you can think about them as benchmarks or mini apps that we basically want to characterize as much as possible from the source, the application, and then ensure that we produce the correct results. And there are different rules on how we can run the benchmarks and validate the results, as well as what are acceptable the inputs and conditions that we want to do when we run when people run these benchmarks on an architecture. as well as rules on how we can report these results to the community, and to have a valid run that can be verifiable. And then there are like the benchmark has a hierarchy is designed where we have a suite called SPEC-ACCEL, and SPEC-ACCEL contains many benchmarks written in multiple programming models, and one of them is OpenMP. And then we have different data sizes that we can use for the benchmarks, and components are the specific benchmarks numbers that we use. And so in the context of SPEC-ACCEL, the OpenMP 4.5 benchmarks are the ones that are in the 500, has a 500 numbering. So when you see that, you will know that that's OpenMP 4.5. So we basically have two sets of runs that we can run the benchmark. One is the base run and then the peak run. And on the base run, we are very conservative on what flags and what is the ordering of the constraints on what a compiler can use to run the benchmarks. And then in the peak configuration, we're more we give more freedom to the compilers to in terms of specifying compiler flags and configurations to be able to give us the best performance that they can on a given platform. And we try to normalize the compiler switches for the benchmarks for the base runs, and there are like only very minimum switches are allowed, and we call portability switches that may help the benchmark to run on different platforms. In addition to that, the benchmarks can also be measured in the context of power at the node level, and there's also a way to score them in terms of power constraints. So, so going back, so what is a distribution? Is like this is a group effort. We also have votes and so on about how we reach consensus on when we develop the benchmarks, and we have technical and discussions as well as management discussions, and there are like different rules that we can do to do this. So SPEC-ACCEL was released in June 2017, and the 1.2 benchmarks, and we have that benchmark that we can use in the context of the same benchmark being developed in OpenCL. We have a benchmark in OpenACC and a benchmark on OpenMP4. And the goal is to make it portable across architectures and accelerators. And that the rule is that the benchmark must pass with at least 2 compilers to be able to be approved. And the benchmarks only target 1 accelerator per run. And we use it to evaluate the performance portability of the programming model. So our experience when we started to develop this benchmark, so we started as soon as we started to get OpenMP 4.0 in compilers, and at that time everything was very new. And we were starting to understand how we could program OpenMP. And as people joined the consortium, we started to play around with the different programming styles. And there were like programming styles that were SIMD centric, where we could just basically express all the parallelism in the context of target SIMD, or we could develop other more like thread level centric. We're using nested parallelism, and but at the end we all agree as the standard move forward that the best way to approach this was to use the combined directives that whenever possible with loop collapsing, because that seemed to be what gave us the most profitability in terms of performance portability, and give us a little bit more choice to the compilers to produce the correct code. So we developed, and it was we had so many discussions with the vendors and the different people, and we finally agree on a consensus. And we did port these benchmarks with OpenMP 4.0, but then at that time OpenMP 4.5 was out, so we decided to skip 4.0 and just target directly 4.5. And then we reevaluated these benchmarks and in the context of 4.5, because there were some semantic changes between those two specifications, and then we continue the development. This is the list of benchmarks that we are targeting. Most of them come from a well-known, other benchmarks that are well-known that has been ported to OpenMP 4.5, as well as other ones from from Mini Apps and Rodinia. One of the key things that that we wanted to talk about is that when we started to develop the benchmarks, we wanted to evaluate how the OpenMP accelerator we can be as performance portable as possible, and we rely on trying to push the limits on the compilers to be able to write the code in a performance portable style. And what that meant was that for each parallel region, we didn't specify number of teams or thread limit or number of threads or SIMD length or distribute or loop schedules, with the idea that if we just write it in a style and we can test it on multiple architectures, then we will be able to leave that to the compilers, and then they will become smarter to help us to provide a good implementation values for different architectures. Although we understand that to tune these codes, we will have to specify some of these. But the goal here was to improve the compiler support or base the optimizations in the compilers. So we didn't specify them with the goal of achieving as much performance portability as possible. So we use significantly the combine loop for whenever we need it, and then the loops that we use the target teams distribute parallel for SIMD collapse n, so we can so that will give us the flexibility of the compiler to pick different scheduler to the loop nest. And for the loops that we could not collapse, we follow the strategy of putting outer loops with teams distribute and parallel for, and the inner loops with SIMD. And so basically, one of the ideas was that to specify this, we rely heavily for the loop nest that we could on the collapse clause to specify the parallel potential that we can achieve on a given platform. So one of the things from our experience was like reductions was a big issue when we moved from 4.0 to 4.5, because we needed to add a map to and from to the scalars. That in 4.5 scalars become first private. So that was one of the things that we have to change extensively in the benchmarks. The other experience that we had when using OpenMP 4.5 was that we tended, since we didn't quite, at the time we were using the program model, we were, to be safe, many people or many members try to do a little bit of over-privatization, where they will privatize variables at multiple levels when it was only needed at one level. And that created more memory overheads and so on. So that was kind of like a common mistake when we were developing the benchmark. So we basically had to retune the benchmark so that we could specify correct levels of parameterization that are efficient. And then the other challenge in what we do with OpenMP4 is that people, when they're moving codes to GPUs or the target teams, they come from, for example, OpenMP 3.1, where there are like implicit barriers at the end of the OMP4, but when they start to use things like teams distribute parallel force or things like that where the distribute doesn't have the barrier at the end, then it tends to be creating some mistakes, and we have to ensure that this loopness doesn't have dependencies across them, so that we can certify that, and to do that, the only way to synchronize across teams is basically through the target construct, because we know at the end of the target construct that all of the threads are complete their execution. So if we want to merge target teams distribute parallel force, we can do that, but only whenever it's safe to do. And there were cases where we had this issue that we uncovered like race conditions throughout the benchmarks because we were not synchronizing this correctly. So it's something for developers to be conscious about, and we already know about this, but sometimes it's not very obvious for some people when they move to OpenMP 4.5. So the other challenge that we encountered was that when we tested these benchmarks, we wrote them, but we don't have a compiler that works on, let's say, all the platforms, basically. We have a compiler that works on Xeon 5, other works on GPUs, other works on multi-core. And what happens is like OpenMP is lower differently sometimes, or they pick different implementation specific values. Just for example, one of the clauses that they pick a specific value is the number of teams if we don't specify any. For example, in the Intel architecture, the number of teams become 1, and then all the parallelism comes from the parallel for SIMD. And so when we tested things like that, it kind of worked correctly on one platform, but when we move it to things like GPUs, where we have a bigger number of teams, we uncovered that there were some race conditions across the teams. So when you write OpenMP 4.5, you have to be conscious of don't declare success if it works on only one platform. You might want to test your code on multiple platforms to make sure that you are satisfying all of the semantics of OpenMP, because it's very easy to hide data races on one platform that may not appear in another one, because the way compilers are dealing with the lowering or the implementation specific values. And then the other challenge is like different compilers have different, even within one platform, compilers can have different strategies to lower some of the directives. For example, Cray may have a strategy. There are different strategies that compilers to treat SIMD on GPUs, for example, and understanding those very well is important, because if we want to achieve performance portability within the same platform across two different compilers is also important that we need to focus on, so that when we write a code, it performs well on one platform with multiple compilers. That's something that is important that we have to achieve. But in this case, sometimes there are like different implementation strategies, so we have to be careful about that. And then debugging makes it a little bit hard when you have different strategies for lowering OpenMP. And yes, and this is, and sometimes testing on multiple platforms, different compilers, may uncover different correctness issues with the codes. So at the end, we ported all the benchmarks, and successfully we have all produced the correct results. And SPEC, ACCEL, they publish all of the results of the benchmarks, and you can go to their web page where you can see the OpenMP results, and then you can see that all of the benchmarks and implementations that are being tested with different compilers and different platforms, and you can see how these benchmarks were compiled and tested, and the benchmarks contain C and Fortran, and different testing centers provide information about that. So one thing to notice is that to be able to publish results here, all these 15 benchmarks must pass on a compiler and a given architecture. So there is, so if that's not true, then the results cannot be published via SPEC. So that's why we're still in the process of adding more results as compilers are starting to tune for the benchmark as well as for correctness as well as performance. You can see that, for example, one of the platforms, first platforms that we are reporting is the CM5 or the KNLs, and then you can see that we can get speed ups across against the reference implementation, and these are very important for vendors to tune their compilers and implementation. So what we want to say is, like, these benchmarks are very new, especially the 1.2, and right now we only have 16 reportable results, as we said previously, compared to hundreds that they are for other benchmarks. We still don't have official results for OpenMP 4.5 offload on GPU. We have compilers support OpenMP 4.5 offload on GPU, just as today in the morning, Catherine O'Brien show you some results of some timings of some of these benchmarks run on GPU, but we're still working into getting the 15 run correctly on the GPUs, and we think that by the end of this year we will hit the milestone of having a complete set of benchmarks that runs on GPUs, and part of the reason is, like, it's just the evolution of the compilers, as well as some vendors just got access of these benchmarks until recently because they were not SPEC members. So it was very hard for them to get their hands on it, but now they're already addressing all these challenges. So the goal of the benchmarks, as I mentioned, is to tune to the target architecture. That's what we really want to do, to force the compilers to be as smart as possible, and then the compilers are developing things, different strategies. Are still deciding on what are the strategies for different architectures, and so co-designing something performance portable. There are many variables going on from the point of view of the programming model, but also the implementation, as well as what is profitable on a given platform, and so on. You can obtain and install the benchmarks, perform your own run, so supply a hardware description, and then submit a report, and it's going to be reviewed, and then we can publish the result. So that's kind of like the period. If your center is interested in evaluating them and getting results that we can compare with other compilers or platforms, you can run and use these ones. And I want to mention that since these benchmarks were just released, we're kind of like looking at the next generation of benchmarks, which is basically wants to focus on hybrid programming in terms of MPI plus X, and that X we think is OpenMP. So we're looking for benchmarks that exploit multi-nodes as well as heterogeneity in the node. We're looking at benchmarks that also support multiple accelerators per MPI task or rank, and so that we can focus in terms of multiple accelerators as opposed to a single accelerator benchmark. We also are looking for benchmarks that are representative of the scientific field. That means benchmarks that have computational motifs that are relevant today and that we need vendors to optimize. So what it means is like a lot of your efforts that you're doing in terms of mini apps, of experimenting with OpenMP 4.5, could be useful if some of them could donate some of these benchmarks to the SPEC organization so that we can continue tune these benchmarks via compilers and co-design it with the platform. Submissions are also encouraged, and there is also, the SPEC offers support for some of the benchmark developers by providing some a little bit of financial support to help them go in the process of preparing a benchmark and make it available for the suite. There is a website for that, and with that, if you have any questions. Correctives.
Performance benchmark. Are there any correctives?
Oh, correctness. Yes, absolutely, absolutely. So part of the benchmark, at the end, the benchmark has to be verifiable numerically. So when they complete the benchmark, they run, the code is verified. The results are verified numerically. So yes, that's part of the process, that a benchmark has to be verifiable.
So you're not kind of also the oversight, like an OpenMP validation ways. So are there any kind of configuration in that direction?
These benchmarks, we tend to focus it in terms of performance. The OpenMP validation suite effort that we're starting as well, it's a different project, is related more in terms of functionality. So ideally it will be hand in hand, the different levels of testing, one functional or one's more performance oriented, yes. But we should, the more we can provide to the community, the better, yes.
I think maybe in the beginning you said that for some of the target tasks, y'all are not specifying the number of teams.
Right.
We're leaving it up to the compiler. I was wondering if you conducted or would conduct some tests where maybe you choose a reasonable value for say the number of teams or number of threads, maybe to test it live itself to kind of fix that parameter across all compilers to see how they kind of compare.
Right. Yeah. So for the base benchmarks, no, but for the peak benchmarks, yeah, that is possible.
Yeah, I was just wondering, this is maybe just a question, since you have a lot more experience than we do. One thing that's never really been clear to me, at least, is like when we're running on GPUs, like what would be the difference really between like parallel do or SIMD? So like if we have a combined construct where at the end, we could say parallel do, or we put SIMD, or even parallel to SIMD. For me, it was never really clear what SIMD meant for a GPU. Like, I just kind of always thought of it as like GPU threads that are there, and we would like parallel do and take care of that. Like if we have a target piece distributed and then a couple of nets of loops in, we might put like parallel do around the loop. I was just wondering if maybe you've seen instances where SIMD actually means something or is that something different?
Yeah, so this is currently a challenge as OpenMP as a programming model can be satisfied many ways, right? So SIMD can be implemented using different strategies, like mapping them to either warps or things like cooperating threads, and vendors are still deciding what is the best strategy for that. And part of the reasons why we still haven't yet the GPU results is because compilers are getting to the point where they're deciding what's the best optimization strategy for those type of constructs on GPU.
Yeah, I can answer a little bit. Last thing with the loop is declaring the programmer saying those loops can be, or those iterations can be independent. But when a loop is inside within the loop, it's basically saying they're independent within the vector, okay? So that you could actually be operating. So it's a little less, okay, but it could be both. You could say, that was one of the things you could say the loop is indivisible or vectorizable, right? And it's also collapsible. So there is a situation where a vector could be something could be SIMD, but it could not be collapsible. That's possible.
Okay, but would collapse imply SIMD? Like collapse them? No.
I would think I have to think about it, but I think the collapse. If it is parallel loop, why couldn't you put that up in the end?
Because we have loops where we just like collapse line. They're all in. So it like implies that it would be.
Yeah. So it's in the combined construct, yes.
But we haven't with Cray. Like we just put collapse line.
And then you got also the
I think they were taking care of it. I hope, but I'm not 100% sure. Like we look at the compiler listings and they say that the loop is being partitioned over the GPU thread. So
yeah.
It seems like it was.
Yeah.
There was a talk by Simon Smith last year, and he recommended the target teams distribute parallel for assembly, and depending on the instrumentation he used, he talked with parallelization of those constructs as far as I remember.
Yeah. So part of the so it's kind of like an optimization problem. So the goal of the combined directive is to give as much flexibility to the compiler to pick how to implement the parallelism or the schedules in the loop nest. But what we're seeing is like that the reason why this benchmark exists is because the vendors are going to look at them and then they're going to influence their implementations for performance. So Cray, we're going to look at this and will make it go fast. So the goal is here is part of the reason is yes, the specification is good. It's already good enough. It's just right now is what are the best strategies for performance while being performance portable in multiple architectures.
Yeah, I think it was our committee's goal to try to use the best practices. And that's very vague. What is really very objective as to what is sort of best practice. But in the one case where we had controversy, I think we 3, because all things could be plus MD, whereas when the compiler wanted to just treat it as class 2 plus vectorize in the inner loop. But so I try to say that what you want to do as a programmer is be descriptive as to what parallelism is available, and then let the implementation deal with it, because it may not have the case of the GPU, it may not have vector instruction, but it will be able to teach use the SIMD in some form, but the SIMD also has some constraints that could actually limit the parallelism because of dependence on the previous vector. Right? So it really comes to the situation of trying to just the best practice is to describe it as much parallelism as the programmer tell us through the practice, but the most amount of parallelism that's available to let the implementation deal with it.
So for performance portability, yes, but the nice thing about OpenMP is like you can specify, you can tune if you want to pursue more platform-specific optimizations. So.
More questions? Okay, I have a last. What is the process of reporting bugs in a benchmark? So if I find, it might be either a bug that the result is incorrect or something like that, like there is somewhere literate, or a portability bug like on my architecture, it would be better to have a different pragma there. So do you expect portability bugs and what about
Yeah, so this depends on like if you're a SPEC member or not, or a SPEC user, right? So in your case, you're a SPEC member. The organization is a SPEC member. So usually we basically send it through. We discuss them through what the organizations are reporting as problematic.
But I think it's important to make a difference between the bugging implementation and the bugging expansion. An implementation bug is not much SPEC can do.
Oh, yeah.
So I was asking about a bug in an application.
In the application, yeah. Yes, because we imagine that as we test these benchmarks across in multiple platforms, we may, there may be some data risks. We don't know. So far, we did our best we could to test. Yes.
Okay, so let's thank Oscar again.